based off our conversation about rotational kinetic energy, because an object has rotational kinetic energy, that means it can do work. So what that means then is that rotating objects, or forces which rotate a system, can be used to do work. So we now want to know what is then the analog of work. So how do we rewrite work in terms of the angular quantities? So to do this, let's consider we have something like this, a pulley. So here is my pulley. And let's say I have a cord wrapped around my pulley, and I'm going to pull that cord, say, down in this direction, causing this thing to rotate. Okay? So let's say initially, here is my cord. I'm going to apply a force down on it in this direction, so let's call that F. And I'm going to apply that force so that at a later time, I'm going to move this thing by some distance of, let's call that delta x. Okay? So in this case, after I move this thing by the distance of x, I'm applying the force still in the same exact direction. We're then going to cause this thing to rotate, which means that this thing is going to rotate from an initial position, where this is our initial position, where this thing is now going to move down to this position, so that this is going to undergo this amount of distance. So as I pull this thing down, this point is going to move over to here. And so this is point A, this is point B. So at a later time, point A is going to be here, and point B is going to rotate to this position. So what I want to know then is, how much work did I do? Well, first, if I'm pulling this thing down in this direction, I know I'm doing linear work. So in this case, we know that the work is equal to the magnitude of the force times magnitude of the distance times cosine and angle between the two. In this case, since I'm pulling in the same direction as my displacement, so in this case, my displacement vector is in this direction, the angle between the two is simply 0, so this is the same thing then as the force times the distance. Now, other things to note. So first off, what I know is, according to the wheel is rotating due to the fact that I'm applying a torque to it. I'm applying a torque because this force I'm applying here is exactly the same at this point, which means I'm applying a force in this direction. Then I have an r vector which points from here to here, so this is my r vector. So in this case, I know I also then have a torque acting on my system, right? Because these two are at a 90-degree angle. The other thing I know is that what? Here, I'm going to cause this thing to move a distance of s, right? Where this is going to be my arc length, s, at which this thing undergoes. But what I know is that s is the same thing as delta x. Right? So again, if I'm causing this thing to move from this point to this point, which is the same thing as the distance I move across here, then the distance this thing has traveled is equal to the arc length, but that must be equal to the same distance at which I pulled in this direction. So I know that delta x here, sorry, I should call that delta x, not r, is exactly the same as that arc length. Now, what I know is that arc length, by definition though, is what? The radius of this object, let's call that capital R, times the angle at which this thing has subtended. So let's call this a delta theta. So in this case, I can say that S is the same thing as delta theta times R. So let's rewrite that. So this then becomes what? F times R times delta theta. But what I also know then is what? F times R, since this thing has a torque acting on it, F times R is the same thing as simply the torque. So I can rewrite this then as the torque times then the change in angle. So this is the work done then by a constant force, i.e. a constant torque. So this is only true when F is equal to a constant, which means that tau is also equal to a constant. These two things have to be constant. Well, what happens if I don't have a constant force? And if I don't have a constant torque? Well, what we know way back when is to find the work when we have a non-constant force is we have to integrate then over the distance at which we're moving this thing, which means in our case, we then have to integrate over the change in angle. So when we have a non-constant force, the work then is going to be equal to the integral of the torque integrated along the angle from the initial angle then to the final angle. So this is when the force is not equal to a constant, which means torque is not equal to a constant. Now, going back to what we did back when we talked about work, what we said was that by the work-kinetic energy theorem, the work was actually related to the change in kinetic energy. So the question is, now that we have a rotational work instead of a linear work, is this also still true? Is the work done on the object still equal to the change in kinetic energy? Well, let's find out. So let's start off again with our definition. So we have work is equal to the integral from the initial angle to the final angle of the torque integrated over the angle. Now, we know torque, though, by Newton's second law. So if this is the net work, this is going to be the net torque, where again the net torque is simply equal to the sum over all the torques. We now know from the angular version of Newton's second law that the net torque is the same thing as the moment of inertia times then the angular acceleration. So let's plug that in. So it's going to be equal to the moment of inertia integral over the angle of the angular acceleration integrated over the angle. So now what? Well, we know that the angular acceleration by definition is equal to the rate of change of the angular velocity. But we also know that in this case, since the angular velocity is changing with respect to time, but the angle is also changing with respect to time, we can then use our chain rule to rewrite this then as how the angular velocity is changing with respect to angle times how the angle is changing with respect to time. So I can rewrite this then as d omega d theta times then d theta dt. But d theta by t by dt, by definition, is the angular velocity. So this is the same thing then as the angular velocity times the rate at which the angular velocity is changing with respect to the angle. So let's plug that in here. So this is going to be the same thing then as moment of inertia times the integral from the initial angle to the final angle times the rate at times the angular velocity. So this is the instantaneous angular velocity times the rate at which this angular velocity is changing with respect to position, or angular position, times then how that angular position is changing. Now, these two things are the same, so we can cancel those out. So this is going to be the same thing, then there's moment of inertia, times the integral of the angular velocity integrated over the angular velocity, from the initial angular velocity to the final angular velocity. That's the same thing as 1/2 the moment of inertia times the final angular velocity squared minus the initial angular velocity squared. Going back to rotational kinetic energy, this is then equal to the final rotational kinetic energy minus the initial rotational kinetic energy. So this thing says that this is indeed equal to the change in rotational kinetic energy. So all this means then is that our work kinetic energy theorem still is valid even in the context of rotations. Where here, the only difference is now that the work is being done by the torque, causing this thing to rotate by about an angle, and this is now the rotational kinetic energy itself. But what about the power? So remember, power, by definition, is the rate at which work is being done, or the rate at which energy is being transferred from one type of energy to a new type of energy. So, what about the power? So let's talk about the power. Well, we know power, again, is equal to the rate of change of work. So the time rate of change of work. So in this case, this is then going to be equal to the time rate of change of the torque times the change in angle, if I'm considering a constant torque. If torque is equal to a constant, I would factor that side of the integral, and then this thing would simply become equal to the torque times the rate of change of the angle, but we know the rate of change of the angle is simply the same thing as the angular velocity. Now, it turns out this is actually also true for instantaneous, so this would actually be the average power. Even if I had a non-constant torque, this would also be the same. So notice here that this is the same thing as the instantaneous torque, instantaneous, and this is the instantaneous angular velocity. So the power then is simply the same thing as the torque times the velocity. Now let's contrast that with the linear power. So remember, linear power was the same thing as the force dotted by the velocity. And as long as these two things were in the same direction, this was simply the force times the velocity. So again, this has exactly the same structure. So again, using our replacement scheme here, the force goes to the torque, the velocity goes to the angular velocity, so it has identically the same structure. So it has pretty much identically the same meaning to it. So let's do one quick example of this and see how all this works together. So this says that we have this following picture. So we have three masses of equal mass. So this is N, M, and M, all spaced exactly the same distance D, which is spaced the same distance D away from the pivot point. So this is my pivot point. So that this entire thing has an entire length of L, where L in this case is equal to 6 centimeters. And then each one of these has exactly the same amount of mass. So the mass is equal to 0.01 kilograms or 10 grams. So what we're going to do is we're going to cause this thing to rotate with an angular velocity in this direction. So what I want to know then is how much work is required to change the rotational rate from part A, the initial angular velocity equal to 0 radians per second, to the final angular velocity equal to 20 radians per second. Part B, initial from 20 radians per second to a final equal to 40 radians per second. And then finally for part C, initial equal to 40 radians per second to a final of 60 radians per second. So we want to know how much work is required to do this. So good. So good. So before we consider each one of these individual pieces, so just remember that again, net work is equal to the change in rotational kinetic energy, which is then equal to 1/2 the moment of inertia about the pivot point times the final angular velocity squared minus the initial angular velocity squared. So the first thing we need to do is determine what is the moment of inertia. So what is the moment of inertia about the pivot point? So first things first is to note about moment of inertia is that a moment of inertia is actually additive, which basically means that if I have this object here, which is rotating, and then I'm going to take this object and glue it on top of that, so now this whole thing is going to rotate, that the total moment of inertia of this entire object is simply the sum of the moment of inertia of this plus the moment of inertia of this, all about exactly the same pivot point. Okay? So what does that mean? So that means that the moment of inertia of this entire system is going to be the moment of inertia of this rod plus the moment of inertia of this mass plus the moment of inertia of this rod plus the moment of inertia of this mass plus the moment of inertia of this rod plus the moment of inertia of this mass. Now, since I didn't tell you the mass of this guy, or this guy, what that means then is that we're going to consider them to be massless, which means the moment of inertia for all three of those objects is simply 0. Which means that this is going to be equal to the moment of inertia of the first mass, let me call that 1, this one 2, and this one 3, plus the moment of inertia of the second mass, plus the moment of inertia of the third mass. Because again, each one of those rods is simply going to give me 0, because they're massless. Now, each one of these masses is what we're going to consider to be a point mass, because I didn't tell you anything about the size of it, so I'm just going to use it as a point mass. And the moment of inertia of a point mass is simply equal to the mass of it times, let's do it that way, L squared, where L is the distance from the pivot point to where that mass is. So in this case, this one has an L of D, this one has an L of 2D, and this one has an L of 3D. So let's put all that together. So it's going to be the same thing then as M times D squared plus M times 2D quantity squared plus M times 3D quantity squared. Now, if I square this out, all the m's are the same, all the d squareds are the same, so we can factor that out. So it's going to be the same thing then as m times d squared times 1 plus 4 plus 9, which is the same thing as 14. So the total moment of inertia of this object is simply 14 times the mass times that distance d squared. Now, the other thing I know is that d, because I didn't tell you d, I only told you L, is d is the same thing as 1/3 of L. So let's put all that together. So finally, what we get is that the moment of inertia about that pivot point is 14 times m times L divided by 3 plus d squared, which is the same thing then as what, 14/9 mL squared. So good. So finally, putting all this together, we can then say that this is the same thing that as 14/18 of the mass times the length squared, all times the final angular velocity squared minus the initial angular velocity squared. So this is the network which is done for each one of those individual sections. Good. So finally, all we have to do is plug in our numbers, and we can then determine the network. So let's look at part A first. So for part A, the network is then going to be equal to, so after plugging in my numbers, this works out to be 11.2 millijoules. For part B, the network then is equal to 33.6 millijoules. And finally, for point C, this is equal to 56 millijoules. So notice each time it's moving fast, it takes a lot more work to get it to move faster as opposed to first starting it off. And the reason for that is that it goes its velocity squared. So to get it to go just a little bit more higher velocity squared, it's going to take a whole bunch more work to get it to go faster because it's already moving fast and it's going to take me a lot more to actually move it to go faster.